a talk by Professor Mark Gahegan. Mark is the Director of the Centre for E-Research at Auckland University and Professor in the Department of Computer Science. Prior to that time, he spent about 9 years as the Associate Director of the GeoVista Centre at Penn State in the United States. He's written more than 100 peer-reviewed articles and given over 110 invited talks. And he's been the PI and co-PI on about 40 funded projects, probably many of them funded by Cliff, potentially. And he serves on the editorial board of about 9 journals. So very pleased to have you here, Mark, and looking forward to hearing your talk. So thanks.
Thanks very much. Well, thanks very much, everybody, for being here. This is the earliest I've ever had to give a talk in my life. I suppose I've been very blessed so far. Can you hear me okay? And I'm pointing this up there, down there, anywhere. I thought it would be useful to have a look at the big picture around cyber infrastructure in the geosciences. It's an issue that's been bugging me for a number of years now. When I was in the USA, I worked with a lot of very committed domain scientists and computer scientists trying to build infrastructure. I've since become the director of e-research at an institution, and what I see now most of all is people who aren't involved in any of these infrastructures at all. They're scientists who work by themselves, who are incentivized to work by themselves, who don't see a need to join in with any other bigger group. And I've been wondering about the dynamics of that. And so really that's what my talk is about. And on the way, I'll look at the geosciences as an exemplar domain and look at some of the very specific demands in terms of data and compute that this domain has and why it's difficult to build a cyber infrastructure for the geosciences as opposed to the biosciences. I think there are some differences. And finally, I think the responsibilities of such an infrastructure, which I think is often downplayed. We, as researchers, have some responsibilities to our discipline. We are not capitalists in that sense, that we can simply exploit it, at least not if we want it to do well. So I'll talk about going from almost no data in the geosciences to having far too much data in about 40 years. Then we'll look at some of the challenges involved in the geosciences around data and compute and community. Oh, and there we go. And then I'm into the first slide. This is what information gathering in the geosciences looked like 100 years ago. This is a picture from 1912. That's the Bavarian pigeon core you can see over there, with a little camera tucked on the belly of the bird, works by clockwork and takes pictures as it flies over the terrain. Used extensively in the First World War. Very poor spatial and spectral resolution on this sensor, but nonetheless was one of the first remote sensing platforms to be deployed. And over the next 100 years or so, this is a picture of the brand new Landsat satellite, not yet launched. This is a picture of some of the more recent unmanned platforms where you can basically put any sensor you like on the platform and fly it wherever you can. Things have changed a lot. The amount of data that we've got has multiplied accordingly. And it might be interesting to think about, well, how much data do we have as a community, taking the earth sciences broadly, and how does it compare to other fields? Are we a tiny part, or are we massive? And I think the short answer to that is we actually don't know. As a community, there's very little work done on how much data we actually hold. And because we're so dispersed, as was mentioned yesterday in that excellent keynote talk, we're so dispersed and funded by different bodies, we probably don't actually know how much we've got. Well, NASA in its remote sensing program has about 4.2 petabytes. We know that. We probably can guess that there are similar sized collections in Asia and in Europe. And this is mostly satellite data. It's not map data. It's not field data. It's not geophysics. It's not ground surveys. It's not instrumentation, which I suspect dwarfs that 4.2 petabytes. Over time, on a year-by-year basis, I suspect also that just like other cyber infrastructures, our own data holdings are probably doubling every year or so, perhaps every 18 months. In some communities, they're doubling faster than that. In ours, I would guess, and it's just a guess, once a year, probably. Then there's the volunteered data, which we're only just beginning to understand how it might play a role in the geosciences. The stuff that can be gathered from smartphones, from small apps, from small sensors that we can easily deploy and fund. And then there's the long tail of dark data. And by that I mean all the stuff that's not on the net, that's gathered privately by government agencies with three-letter acronyms who don't typically share data. And I suspect that that's probably a mountain that's equally big. So it's a lot of data. For example, one could ask the question, thinking about emerging data paradigms, what do finding traffic bottlenecks, computing the epicenter of earthquakes, tracking influenza pandemics, and performing land cover classification, what do these four activities have in common now? Anybody guess? Good answer, but that wasn't what I was thinking of. Another good answer, not what I was thinking of. Yeah. Crowdsourcing, thank you very much. All of those things you can do from your phone. All of them. Traffic bottlenecks are done just by tracking how fast phones move in traffic. Earthquake epicenters, each one of these has an accelerometer in it. You can, and it has been done in the USA, you can compute the epicenter of an earthquake from the accelerometers in iPhones. You can track influenza pandemics, some quite good research done on that, by looking at the pattern of searches and where people are when they make those searches from their mobile devices. Tells you, it's about a 90% accurate predictor of the state of a pandemic. Land cover classification is a little bit more tricky. You can do it by photos, but you can also do it by sound. It turns out that very good indicators of land cover classification are the sounds that you hear in the terrain. Birds, cars, insects, all of those have unique signatures that are just as useful, as it turns out, as the signatures that come from spectral information from space. That really turns the problem around, how we might do some of this geoscience. And we've only just begun to explore some of the possibilities there. That's not what my talk is about, so I'm going to park that and move on. So how does all this compare to other science disciplines? Well, the Large Hadron Collider is typically put forward as the big science app, the one that produces all the data, the one that produces a 20-kilometer high stack of DVDs every year. I think actually the Earth Sciences is right up there in terms of that much productivity. It's just that we don't have a single central infrastructure where we might put all that information. But what if we did? What if we had something like EarthCube? Well, this tells us that over time, if we really we're going to capture all of that information, we've got to be thinking at scaling to almost impossible amounts of data. Now, we don't have to hold all of that data in one place, of course, but we need to be able to federate at least to truly massive collections, tens of petabytes per year. That's our aspiration. That's where it should be as a community. And I don't think we're thinking quite at that scale yet. Genomics is also put forward as the one that's leading in terms of the production of data. Now, in the genomics community, the data holdings that they have double every 6 months. Imagine that. Imagine those of you who provide infrastructure. Imagine that you had to double the amount of disk that you held and operated every 6 months from now until forever. Again, a hugely daunting prospect. And I don't even think we've begun to imagine the scale. Now, I would suggest to you that in the geosciences, our data holdings are probably increasing at about the same speed. Happy to talk about that afterwards if you'd like some evidence. So what are the challenges around big data for cyber infrastructure, and in particular for geoscience? Well, firstly, there's the unprecedented volume. Generally speaking, our ability to store data was surpassed by our ability to produce data about 5 or 6 years ago. So now, as a science community in general, we're producing more data than we can store. And we haven't quite figured out yet what to store and what to throw away. So that's one challenge. The second big challenge, and this is especially true in the geosciences, is figuring out how to describe what we have so we can find it again and other people can find it again. If the earth sciences were not such a situated, contextual discipline, this problem wouldn't be so hard, because we could agree on an ontology for our domain, hopefully, or maybe just a few. And we could mark up all our data collections according to this ontology. I would suggest to you that in the geosciences, the problem is not that we don't have an ontology. The problem is that the science itself is so situated, so nuanced, so interpretive, so discursive, that it's very, very difficult to describe meaning in any useful way. The kinds of hierarchies that are typically built to describe meaning by starting with a universal object or category and breaking it down into smaller and smaller categories, they don't help us at all. Every geoscientist knows how to take something like a basin and connect it up to the higher level semantic objects. But it's the complexity of how you understand a basin and its situatedness and how it's been classified and how we know it's been interpreted in a particular kind of way. Who's telling the story about its evolution? All of that is what's required in order for one geoscientist to take the data from another and use it reliably. And I don't think we've really begun to understand that problem well either. But if we could describe our data that well, then it should be possible to build the search tools that we would need to find the information that we might require and to be able to reuse it. So we'd see data reuse increase and sharing of data, and perhaps some shared ownership of data and the idea that the community really can take a pride in these kind of data resources. Fourth question related to the volume of data production is figuring out what we don't need and what we can throw away. And again, this is a problem that we haven't really got to grips with yet. We can't keep it all, so what should we keep? Where in the data are the useful signals? Now again, if you have a really well-posed question, then it's possible to find an answer to this kind of dilemma. If you know what you're looking for, you can do some machine learning to figure out what it is, or statistics to figure out what it is you should keep. What carries the best signals for you. But if you don't know the questions you're going to ask yet, it's very difficult to presume. And one of the issues that we have is we don't know the questions yet. You couldn't have predicted 30 years ago the questions that earth scientists would be asking today. About carbon sequestration, for example. That wasn't really on the radar 30 years ago. A few people were doing it, but it wasn't a very big question. And its relationship to land cover change wasn't a very big question, but it sure is now. We haven't thought about how we organize our research around those questions, and we haven't thought about how to deal with questions that we haven't thought of yet. Those unknown unknowns, as famously quoted yesterday. Then we have to figure out how to govern those collections well. And here I think we're truly missing the point so far too. And to make the point, I would say, well, what university teaches its undergraduate students or its graduate students to use these infrastructures well? But they are a member of this community, born into it, and they have rights and obligations back to this community. That's not how we teach at the University of Auckland yet, I'm sorry to say, and I suspect it isn't in many places too. It has to change. In order for this to be a community resource, the community has to stand by it, and that has to start from day one, not when you want funding. So there's Einstein saying something he never really said about big data and the emergent world of large cyber infrastructures, perhaps. But the fourth protocol, as it's being called, data-led science, also provides some really big challenges in the computational side, not just the data side. And if we think about it, we're collecting these massive data sets because we want to compute big problems with them. So we can't really stop at the data and say, okay, well, once we've got data collections, that's great. We have to also think about the other side of the coin, which is how we compute with these big data sets and what the challenges are there. And there are many too. So there's a big but in the middle of all of this. We can deal with the data, but we've got to deal with the compute challenges too. And these are, I think, quite large as well. One of the biggest problems we have in the geosciences is that we have a massive basket of different data structures and data types that we need to integrate together to solve problems. It's not about just scaling up one particular kind of problem. It's about scaling up all of those particular kinds of problems together. We want to understand about climate change and climate downscaling, but we want to do that so we understand how that will affect storm surge in very local areas, a problem that we might be particularly concerned about today. That involves the integration over massive computational scales of all kinds of data types and all kinds of algorithms. The mixed bag is the problem. Our approach so far has been very piecemeal. We've taken a tiny piece of one of these problems and we've decomposed it as best we can and solved it. What we need to be doing is thinking much more about how the pieces join back up together. So again, to downscale and link and to really analyze, we have to figure out how all of these different data types and different ways of decomposing a domain, how they all might fit back together again. So domain decomposition is a very well-studied art in high-performance computing. And the geosciences have been quite good at taking particular parts of it, like this earthquake model from Terrashake, and decomposing it so that it can be solved on some kind of finite solver, finite elements, finite methods, something like that. But how about the effect of that on society, on infrastructure? That involves solving over the domain of roads or the domain of the electricity grid. And that we're not so good at yet. So we know what computational architectures we have, and we know about their uses in scaling. And we know also from high performance and supercomputing research the kinds of data structures that can be decomposed and how well they perform on certain kinds of architectures. But we haven't really joined the dots yet and figured out how to provide an infrastructure that helps us solve these real problems by integrating all of these different parts together. Another question we, I think, need to ask, and in a hurry, is do all our use cases form into this well-understood set of domain decomposition and supercomputing apps? Much of our resistance to scaling in the geosciences is due to the complexities and the multi-resolution aspects of our data. So how do we scale our data? And that suggests more adaptive styles of computing rather than the typical kind of more grid-like cutting and decomposition that we currently use. So I think this problem is still, we're still figuring out the scope of it, and we're not there yet. Obviously, some of those algorithms will give us better benefit than others when we re-engineer them according to how much speed up we can get or how much slowdown they offer and the cost of re-engineering. And again, I think although we can imagine a graph like this one here that shows that there are some algorithms that would be better invested in than others, we're really not sure yet which ones they are. So if we're heading for the top left quadrant up there to get the best scaling and the best bang for our buck, which algorithms would we be working on? I don't think we know. Not in a complete sense. Finally, turning to the community aspects of a cyber infrastructure. The reason that cyber infrastructures fail is because they're not sticky. It's because the community don't feel the need to come back all the time or even to reside in that infrastructure. They use it when they can and then they're off. We need to make them sticky. We need to make them pervasive. So how do you attract and keep a community? What kind of engagement models will work for them? What kind of functionality is compelling? What kind of incentives are there to contribute? What about the perceived continuity of these infrastructures? Every single infrastructure that I've been involved in, that I know of, has a finite life. Typically 3 to 5 years. If you're lucky, it's 10 years. Well, researchers don't think in terms of 3 to 5 years. They think in terms of careers. And if something isn't going to be around in the next 10 years, why on earth would they bother moving to it? Why would they trust it if there's no longevity? So this is a challenge for our funding providers. How do you make an infrastructure that looks appealing because it has long life? And a research community really needs that to invest in it. A research student who's starting off would be looking at, well, how long might this be around for? Is it a good investment for me to join this community? Big problems. There are some great examples of successful cyber infrastructures like Data One, like the One Geology portal, which is great. If you haven't had a look at it, go have a look. Integrated 1 to 5 million geology of most of the Earth. Like Oscope, which has a really good software stack for geosciences services to be developed on, and a few other things that I'm sure Robert will talk to us about later. We can solve some of the semantic problems. We can solve some of the translation problems. We can solve some of the scaling problems. We can solve some of the situated problems of placing research articles in their context within communities. But we have to start bringing some of these ideas together. So here's where we get to the crux, and this is my last slide, the responsibilities. How do we facilitate big and small analysis? We have to reset expectations in a community in terms of how they might contribute and facilitate such an infrastructure. We're trying to create a living laboratory. Now, in the geosciences, I think this is particularly important because unlike chemistry or biology or even the Large Hadron Collider, what we're doing is creating a living laboratory of the planet. It will never be in the same state again. So, as well as doing our science and finding out what happens when you smash things together, we've got to remember how things were, because it's really important to the future of the planet. I think our responsibilities in this regard have not been taken on yet. That's not a value in our community, but it's really vital that we take it on. We have a responsibility here, it's not just take. So that responsibility has to shape our own actions in our infrastructure. The ongoing record is more important than us and our individual research. And I don't think we've got that yet as a community. We've still got some work to do on creating those successful languages and tools that describe our data so reuse can be encouraged. And as I said before, that's more to do with the situatedness of the geosciences than it is about any technical barrier. So I think I'm done. Hopefully there's still time for questions, but thanks for your attention and being here so early. Appreciate it. Don't be shy now. Yeah.
I have a question. So the Earth cube, where does that fit into this, your thinking?
Well, that would be unfair of me to answer, I think. But as I see it, Earth cube is much more of an effort to engage the community first and to ask the community to build the infrastructure rather than the previous model was, which was, hey, as a funding agency, we've got a lot of money, give us your proposals and we'll fund you. And so you end up funding small groups to do various pieces without any real plan to stitch them together and sustain them afterwards. So talking earlier, I think that's the real difference, that the focus is on first building the community and then saying to the community, actually this is your problem, not our problem as the funding agency. Did I get that right? Yeah. Right. So it's not about who can make the most compelling research-related case to get funding, but who in the community is most likely to have authority in the community and respect in the community to build the tools that the community will then use and trust. I think that's it.
So we...
Implicit in your talk, or perhaps I'm reading too much in it, was the need for data curation. You never actually used that word, but it was implicit. And the need for competency centers in terms of the technology and allowing the transition from researchers to being able to use something like high-performance computing. Is that fair? Am I reading too much into the talk to say perhaps the way we apportioned funding between collecting data and actually getting it used might be rethought at this point?
I think so. we're trying to make big integrated data collections so that they can be used in that manner. Otherwise, we just build stovepipes for small bits of the geoscience community like we have been doing. If we truly believe the Earth is an integrated system, then our computational approaches have got to scale to that problem too. And so the use of the data in those really complex models and how the infrastructure can serve data into those complex models has got to be thought through. And that's not just about curation, but a big part of it is. But it's also about throughput. If you want to be able to run massive compute, then you have to think about how you organize your data for throughput and for staging as well as for longevity and archive. So two not necessarily convergent ideas. Yeah.
Ingrid Mason from Intersect. Mark, I'm very struck by the parallel here with issues with transport and long-term public investment in transport. And I just wondered if you had any thoughts about either talking or referring to that kind of scenario with the one that you're actually talking about this morning.
Yeah, that's a very good question. I suppose that's right, in that transport, we all need it to work. And if none of us used it, it wouldn't be funded, and it would crumble. And as a society, we're better off if we use it than if we all try and drive our cars everywhere. So yeah, I think the parallels are, that's a very good observation, actually. Yeah. It might not be necessarily in our best interest to get from A to B as fast as possible, but in the long-term interest of the community, we need to change the way we work. Yeah. Yes, so thanks for that. Good conclusion.
Okay, well,
Thank you.
let's thank Mark.